This is Stephen Yan presenting Lab02. The purpose of the lab is to determine the relationship between the observation distance and the magnitude of the magnetic field of a permanent magnetic dipole. Then, using the data collected, we calculate the magnetic moment of the bar magnet and simulate its magnetic field in VPython. The physical principles used include the Biot-Savart law for magnetic dipoles, which expresses the magnetic field at a certain location in terms of the displacement vector and magnetic moment of the magnet. The reason to include this is because it's a suitable model for a bar magnet, which is an example of a magnetic dipole. Then there's the distance dependence formula for magnetic field, which is presented below. The reason for using this is because it allows the easy calculation of n and k when we have gathered data on the magnetic field and r. Here is a brief overview of the results of the lab. The system being studied in this lab includes the bar magnet and the Earth. The Earth is included in the system instead of the surrounding because it is essentially a giant magnetic dipole, and its effects cannot be neglected. See Figure 2 for visualization. The physical model consists of a bar magnet pointing in the east-west axis of the Earth. See Figure 3. This setup is chosen because the on-axis magnetic field of the bar magnet will be orthogonal to the magnetic field of the Earth, which allows the Bx values to be collected directly without interference from the Earth. Here are some assumptions to be made about the model. We assume that only the Earth and the bar magnet are contributing to the magnetic field at the observation location. We assume that the k term in the distance-dependent equation is constant, which means that r is the only variable. The initial conditions of the experiment is a qualitative one. The bar magnet is pointed along the east-west axis, meaning the x component of the magnetic field from the Earth is 0. For the setup of the lab, I first oriented the ruler towards the magnetic north by rotating the phone until the x component of the magnetic field is 0 and pointing the ruler in the same direction. Next, I located the magnetometer of the phone by performing the following tasks in the slide. For the on-axis measurements, I moved the phone along the ruler and record the distances when Bx reaches specific values. The data are recorded in Figure 8. To interpret the data, we perform some variation on the distance dependence equation by taking the logarithm of both sides. The new equation will resemble a linear function defined by y equals mx plus b. Now we see that the value of n is the slope and ln of k is the y-intercept. N, k, and thus mu can now be determined. Next, for the off-axis measurements, the phone is moved to a position that is deperp in both the positive x and y direction relative to the ruler, as seen in Figure 9. Deperp, the net magnetic field, and the Earth magnetic field are recorded. The data is seen in Figure 10. This data will be compared to the data from VPython in later slides. Let's now look at the coding section. First, I inserted the value of k to calculate mu and define the function for magnetic field. I then created observation locations that are on-axis and perpendicular to the magnet. Following this, I created arrows representing the magnetic field at each observation locations. Finally, I used the deperp values to simulate the off-axis magnetic field. Shown here is the output of the code. As seen, the fields located on-axis and perpendicular to the axis are anti-parallel, meaning they point in opposite directions. At the same distance from the dipole, Bperp is half of B-axis. Let's now compare the data and model predictions. In theory, the distance dependence n should be -3. The calculated n is negative 2.9672. This is very close to the actual value with a percentage error of 1.09%. For the off-axis data, the Glowscript model shows that the magnetic field at 45 degrees should be 6.784 times 10 to the -5 Tesla, while the actual measurement shows a value of 7.017 times 10 to the -5 Tesla. The percentage error is 3.44. Possible sources of error include that the phone odometer 6 orientation might have shifted slightly, or that other weak magnetic fields are present. If I haven't compensated for magnetic north, the X component of the Earth's magnetic field would not be zero and would contribute to the net field at any observation location. This would cause the entire model to be inaccurate. If two identical magnets are stuck together end to end, the direction of the magnetic field would be identical, but the magnitude of the magnetic field would be around twice the original data.